Hi, I'm Krista Campbell. Welcome to the first webinar in our ArcHydro in Action webinar series, ArcHydro in ArcGIS Pro. In this webinar, my colleague Dan Djokic will discuss ArcHydro tools, define what ArcHydro is and what it is not, and take a look at how data makes a difference. Dan will also provide an ArcHydro demonstration. He will share polling results from the live webinar, as well as answer some of the questions that were submitted. I hope you enjoy the webinar.
Hello, I'm Dan Djokic, Water Resource Practice Manager in Esri's Professional Services and ArcHydro Team Lead, and will be leading this webinar series. A little bit about my background. I'm civil engineer by training. All my degrees are in civil engineering, more specifically water resources. I have started as a design engineer designing hydraulic structures for dams, then transitioned to hydrology and hydraulics in order to better design those structures. I ran into GIS while doing my PhD at the University of Texas, and it became part of my dissertation work. After 6 years in consulting and 8 in academia as student, research associate, and professor, I joined Esri about 25 years ago. I have been working on implementation of GIS with our water resources users since. So what we'll talk about today and over the whole webinar series is a reflection of these experiences. To get started, I have 2 polling questions for you. We have 1,000 participants, so we should have good statistics. First, who are you? And then, what is your common GIS software usage? Most of you are in the science engineering group and used mostly desktop with some online sprinkled in. What I will be presenting today and during the whole series is a result of work of many people. Our core ArcHydro team in professional services is small. Christine, Zichon, and I have been around for a while Gina and Ezra joined the team recently. But we build on top of and work closely with many other people within Esri. In our industry solutions, thank you Krista and Mariah for organizing the series, in core product development, Living Atlas team, and many others, so it's definitely a team effort. And as I introduce ArcHydro, you will see that a lot of ArcHydro development is based on our work with our users, so this is truly a community effort. In this first webinar, we will talk about some hydro definitions in GIS context, introduce ArcHydro, what it is and it is not, have a look at some basic ArcHydro capabilities, and talk about the importance of data in the context of hydro analysis. And we should have some time to address a few questions. This presentation will set the ground for the 3 following webinars, where we'll dive into more details on specific ArcHydro topics and ArcHydro implementations. Before we dive in, let's do the second questionnaire. Please let us know frequency of use of our tech and your primary desktop environment. About half of you use our tech daily, and we have fairly even split between ArcMap and Pro users, with very few being in the online environment only. Let's define some key terms. The purpose of hydroanalysis in ArcGIS is to model the flow of water across a surface, to know where the water is coming from and where it will flow to. And to do that, we'll often be extracting hydrologic information and drainage system characteristics from digital elevation models and supporting data. When I talk about hydro in general context, I will be referring to both hydrology and hydraulics and water resources analysis in general. Here is a play on the hydrologic cycle. We start with GIS and characterize the landscape and derive necessary model parameters. We then use hydrologic and hydraulic models to determine flow rates, water surface depths, and velocities. And then we use GIS for result post-processing and visualization, including further analysis based on H&H model results like flood impact assessment. Let's review some of the core hydro tools in Esri's technology. In ArcMap and ArcGIS Pro within the Spatial Analyst extension, there are 12 hydrology geoprocessing tools. Most of these are also available as raster functions in ArcGIS Pro. And in ArcGIS Image Server, these tools are exposed as geoprocessing services that can leverage distributed raster analytics on a cluster of machines for big data processing. I will not talk about all of these functions, but will do a quick review of a few capabilities that you might not be as familiar with. Flow direction is one of the fundamental hydrology functions. It defines which cell will the water move to and is critical in hydroprocessing of digital elevation models. Traditionally, only the D8 flow direction method was supported. Relatively new is the D-infinity flow direction model. It can proportion flow from each cell up to 2 downstream neighbors. Another new dispersive flow direction model is multiple flow direction, or MFD, and is based on maximum downslope gradient. In this model, flow can be proportioned to all downstream neighbors. What this means is that steeper neighbors would receive a greater proportion of flow compared to the rest. The result is a smoother spatial distribution of flow accumulation, particularly in low relief areas compared to D8. And the last function I would like to highlight is the flow distance function that was introduced in Pro 2.1. The tool computes vertical or horizontal distance from cells to the nearest stream following single or multiple flow paths. The tool supports all 3 different flow methods. The vertical flow distance is also referred to as hand, or height above nearest drainage. Combined with flooding depth at the stream, hand raster can be used to quickly determine if a structure will flood or not. This comes in handy in flood inundation mapping, and we'll be referring to the hand method in later webinars dealing with flooding. While we use these core hydro functions in ArcHydro, they are not ArcHydro. So what is ArcHydro? The idea behind ArcHydro is to provide GIS framework for development of integrated analytical systems for water resources. There are several key elements in this. It is a framework, not a solution for a specific water resources problem. It is geared towards analysis and not cartography, and includes the data model, tools, workflows, how to best use the tools for particular use cases, and the community of users with common interests and patterns of use. The ArcHydro GeoNet page is the gateway to all ArcHydro resources and platform to share information and experiences with other users. But let's also define what ArcHydro is not. It is not data, but you can use it to develop different hydro datasets. It's not an H&H model. We do not solve partial differential equations governing flow of water in ArcHydro, but you can use it to support H&H modeling. It is not a solution to a specific hydro problem, but can be used to build one. And is definitely not a black box system. It is designed to be extensible and flexible. But since it is geared towards analysis, you cannot just do whatever and expect things to be correct. ArcHydro started as a project to demonstrate geodatabase capabilities in water resources. It was led by Dr. David Maidment at the University of Texas and focused on the ArcHydro data model and efficient representation of water resources data structures within geodatabase environment. It was released in 2002 as a data model, a tool set, and an Esri press book. It included an initial set of 30 tools developed by my team. These tools were geared towards populating and attributing the data model and for performing some basic analysis like watershed delineation, upstream, downstream tracing. Since 2003, ArcHydro continued development through projects. This included extension of the data model, particularly development of the groundwater component in 2007 and refinement of the time series data structures. We also added over 300 tools to cover different aspects of data development and analysis. These tools were developed through project work and are a reflection of our users' workflows and requirements. Esri provides tool maintenance through version updates and user support. Since ArcHydro is not a product, support is provided via GeoNet and direct response to emails and not through regular Esri product support channels. When you have ArcHydro questions, you will be talking directly to me and my team. Esri also offers formal training classes on ArcHydro that are managed as standard Esri training but are delivered by my team. Basic ArcHydro elements are available for free through GeoNet page. This includes the data model, tools, workflows, and documentation. Most tools are available both in ArcMap and ArcGIS Pro desktop environments. Development of new tools is now primarily done in Pro with port back to ArcMap. Some of the ArcMap-based tools are still in the process of being ported to Pro. For fee offerings include training and consulting, and if you are interested in those services, please contact me. ArcHydro is used extensively. We have about 1,000 downloads monthly, and we have applied ArcHydro on over 100 projects. And something I'm particularly proud of, we trained numerous professionals through over 120 ArcHydro and H&H classes held on 4 continents. So who are the ArcHydro users? Basically anyone who deals with water resources. Here are some of the users that are using ArcHydro in their daily practice. We work with many of them, and ArcHydro evolution over the years directly reflects those experiences. This is a slide I always struggle with in explaining, although I put it together. The intent here is to indicate that ArcHydro has many potential uses in various domains, not to box it into just those uses for those domains. Each time I look at it, I want to add more rows, columns, and crosses. I always find additional uses in other areas. ArcHydro is for water resources and is not a black box, so its applicability is really unlimited. Of course, it cannot do everything, but it can be a foundation for many applications. Now that we have defined what ArcHydro is and is not, let's do the final questionnaire of the day. Can you please check off your experience in using ArcHydro? So most of you are new to ArcHydro, and we have few that have been users for a long time. Let's dive into the foundations of ArcHydro, the data model and the tools. From the beginning, ArcHydro was designed to be a starting point for water resources analysis. Our water resources domain is too broad to be able to make the solution for it. So our approach was to create an extensible system that you can use as a foundation for your specific workflows and needs. Think of it as GIS Lego blocks from which you can build your own water castle. When you install ArcHydro Tools, you get a toolbar and a tool set with over 200 tools. You will most likely never use all of them, probably 20 to 30 tools that are specific to your needs. ArcHydro has different grouping of tools, so depending on who you are and what you do, you will use different set of available tools. Most everybody is going to use the tools that deal with terrain pre-processing and identifier management that allows you to connect one set of features to another. ArcHydro has a whole methodology on how to do that, and we'll talk about it shortly. Once you're done with the terrain pre-processing, then you can do different things. Watershed delineation is often the next step, followed by watershed characterization. For example, what is the percentage of impervious area, or what is the land use distribution within the watershed? ArcHydro has a whole suite of tools for floodplain delineation, including the hidden methodology. We will go into more details in subsequent webinars. And tools for stormwater systems where the water does not only flow through overland system, but also main stormwater structures like pipes and inlets. And there are sets of tools that have been developed for both specific clients and specific model interfaces. As you dive into ArcHydro implementation, there is a lot of documentation to guide you through the journey. All these documents are available via the Water Resources and ArcHydro GeoNet documents page. You should definitely review the best practices document first. It applies to both Pro and ArcMap Hydro implementations. then pick and choose relevant documents depending on the type of work you need to do. In the next sequence, I will walk you through some of the basic elements in development of ArcHydro project that make the foundation for core analytical capabilities. We'll start with the digital elevation model and from it derive drainage systems. First drainage lines and then catchments, areas draining into the drainage lines. Then we can characterize both the aerial and linear features with desired characteristics like slope, elevations, and lengths. Next step is often derivation of node link structure to support H&H models, and then export of GIS data into formats for specific external models if advanced H&H modeling is required. And all that while maintaining the integrity between vector and raster representation of the landscape. On the data model side of things, ArcHydro is based on three key elements. First, unique identifier, and we will use HydroID as globally unique identifier within a geodatabase. Second, linking data elements using the unique identifier. And finally, using tracing to identify upstream and downstream elements. The tracing can be done either via trace or geometric network capabilities for complex drainage systems like stormwater, or using attribute tracing for simpler drainage systems. Let's look at some data model details. We'll start with the drainage lines and assign HydroIDs to them. We'll continue with catchments, areas draining into drainage lines, and assign unique identifiers to them as well. These unique identifiers form the basis for the linking. To establish upstream-downstream relationship between the features in the same feature class, we'll use NextDownID attribute. This attribute contains the HydroID of the next downstream feature. So for drainage line 1, NextDownID is equal to 2, which is the HydroID of the next downstream element. And similarly for the catchments. It is important to note that NextDownID field applies to any type of features, not just lines. To establish a relationship between features across feature classes, we can use DrainID, which is the HydroID of the drainage area draining into the feature. So in this case, DrainID of drainage line 1 is 6, which is the HydroID of the catchments draining into that drainage line. The same data modeling pattern can be applied as our data model becomes more complex. Here is an example where besides the drainage lines and catchments discussed before, we also have drainage points and hydrojunctions added to the model. Drainage points are the outlets of the catchments, while hydrojunctions are confluences and head points of the hydro network. HydroID and related IDs are used to define attribute relationships between all the geodatabase elements. ArcGIS Tools will populate these attributes and will rely on them to perform the analysis efficiently and consistently. So let's look now at ArcGIS in action. To save us some time, I have already started a Pro project, added the DEM, and performed the initial pre-processing. This will save us some time and allow us to focus on interactive part of using ArcGIS. Let's look at the area we are dealing with. This is the Big Bear Lake watershed just northeast of Redlands. It is interesting topography starting at about 11,000 feet, quickly dropping to a few hundreds in Redlands and then draining into the Pacific Ocean about 100 miles downstream. The digital elevation model we'll be using is the USGS 10-meter net that I got from the NHDPlus high-resolution dataset. When you install ArcHydro, you get ArcHydro ribbon and a toolset. Here's the ribbon, and here's the toolset. ArcHydro has many tools for terrain pre-processing. We will use here dendritic terrain with unknown stream locations. It is a model builder that strings together 10 different tools in very specific workflow. If you want, you can edit the model and review which functions and in which order are executed. If needed, you can tweak the model to your specific needs. In this case, I just ran the tool as is. Once the tool is done running, it will generate a number of raster and vector layers. Here are a few of them: flow accumulation and all important flow direction rasters. Here is the polygon catchment feature class and the drainage line feature class. If we look at the structure of those two feature classes, we can see all the attributes that we talked about earlier in the presentation. So for catchments, we have Hydro ID, next down ID, and for drainage line, in addition to those, we also have a drain ID that ties it into the Hydro ID of the drainage area. Both of them have grid ID that tie the vector representation to the underlying raster representation of the feature. This is how we keep relationship between raster and vector representations of the same landscape element. Let's now do some interactive watershed delineation. This is where you can add your own outlet locations and identify watersheds draining into your point of interest. We're going to use ArcGIS Point Delineation tool from the ribbon. I'll click on the tool. It will open the geoprocessing input form. I will click on the pencil to enable interactive point definition. You can also use an existing point in a feature class by specifying the point feature class as the input here. I will zoom into the area immediately below the Seven Oaks Dam and place the point on a drainage line. And I will run the tool. It takes about 30 seconds to get the results. When you run the tool for the first time, it takes a bit longer since we are creating all underlying result data layers, and that takes some extra time. The results of the tool are stored in two feature classes: watershed point with snapped location of the watershed outlet, and watershed poly with watershed polygon for that point. Let's see what these look like. Here's the full watershed. Notice that in the east upper end there is a missing portion of the delineated watershed. If we look in more detail, we'll see that it's really not a missing area. It's a depression that doesn't seem to flow into the Big Bear Lake and is thus not contributing to our watershed outlet. Let's now delineate the watershed for the same outlet, but let's use ready-to-use tools. I'll zoom out, select Analysis, Ready-to-Use Tools, Watershed. I'll use the existing watershed point feature class as input, select 450 meters as snap distance, and 30 meter as data source resolution, and I'll run it. Make sure you don't select generalize, because we want to see the resolution of the underlying DEM, and that you select return snapped points. The results of the tool are stored in two feature classes: output snap point with snapped location of the watershed outlet, and output watershed with watershed polygon for that point. Here is the resulting watershed. Let's rearrange the symbology for the two layers to better see the differences. I'll change the outline. I'll make it red, and we'll put the layer on top. Notice that in the upper east end, what was previously the missing area is now contributing to the outlet. Let's zoom at the outlet and see the differences in more detail. Well, there are some differences that are very close. This is a result of using different resolution DEM and how they were pre-processed. The underlying terrain pre-processing and watershed delineation methodologies are both the same. Differences in results as a function of different data resolution and their interpretation is something that we will talk some more in the following webinars on hydrologic and hydraulic modeling. And finally, we'll delineate the watershed for the same outlet but using ArcGIS Online. I logged into my ArcGIS Online account. I will select a new map. I will zoom in to our location of interest. Select Analysis, find Locations, create watersheds. I will select Interactive Point Location just downstream from the dam. We'll pick 450 meters for snapping distance. Define location somewhere around here. And we're going to run the analysis. The analysis runs for about 10 seconds. And we should be getting the result shortly. And here is our result. The result looks very similar to the ones that we have defined previously using ArcGIS Pro. So to conclude this demonstration, we have used 3 different ways to delineate watershed using 3 different data sources and functions. We cannot talk analysis without talking about data. You have seen in the demo the impact of some terrain processing decisions and available data on the analysis results. Getting good data to support your analysis is always an issue, since the data are used for analytical purposes and not just cartographic purposes. The quality and consistency of the data are critical. And that goes across all the data used in analysis, not just one data set. Also, the quality of the data need to be put in the context of the type of the analysis being performed. For example, while for hydrologic analysis coarser data might be adequate, for hydraulic analysis we might need better data. Data can be split into 2 broad categories. The first category are the landscape data. These are static data that describe the environment with respect to hydro processes such as elevation data, soils, land use, impervious cover, etc. The second category are the hydro data. These are dynamic data related to quantification of water movement through the landscape, such as stream flow measurements, weather and climatological data, and water quality measurements in general. If you have to hunt for the data to be used in your project, Living Atlas of the World is always a good starting point. Many both landscape and hydro data will be available through it. These data are curated, and once you understand the provenance of the data and their viability to support your analysis, you can use them with confidence that they will be of good quality and will be maintained in the future. Living Atlas hosts many data. Like global hydro geoprocessing services we looked at and used in the demo. Soils data, you can get hydrologic soils group that might be useful in your hydrologic modeling. Stream gauge data. There are over 25,000 stations update hourly, mostly in US, but also in several other countries across the world. And live feeds on many interesting variables that are updated on a continuous basis. In the US, USGS and NRCS publish a lot of landscape data useful in hydromodeling. And USGS and NOAA publish a lot of hydro data that might be of interest to you. But often, hydro data are very local, and you will have to discover data locally hidden in some drawer or collect them yourself. And remember, it is not about just each individual data set, but also how all these data put together help you do your job better. With GIS and ArcHydro database design and tools in particular, we try to provide you the infrastructure that facilitates collection and integration of the required data for your hydroanalysis. Correct digital elevation representation of the landscape is critical for successful implementation of GIS to support your hydro needs. This is not just about getting the data, but making sure that their quality, resolution, projection, processing methodology are adequate for what you need to do. For example, if you are doing mass balance analysis for your hydrologic modeling, please don't use web Mercator projection. This is not about pretty picture, but about getting the analysis right. Here's a pretty picture of terrain somewhere in Turkey, but does the water flow correctly over it? That is what it's all about. Another important consideration is how to process the DEM with respect to the analysis being performed. For flooding, filling sinks might be fine since these depressions will eventually fill and water will contribute to flooding downstream. But for low flow analysis, filling might not be appropriate since these depressions are where water will collect during drought conditions, and knowing those locations is critical for the analysis. This is where terrain hydroconditioning comes in. Hydroconditioning is making the water flow over the digital representation of the terrain in the way you want it to flow. It is about developing a flow direction raster that reflects the correct or expected behavior. There are many workflows that can be used to develop hydroconditioned DEM that are captured in ArcGIS Tools. I have demonstrated the basic dendritic processing workflow, but there are many others as a function of the morphology and available supporting data. For example, morphologies where we know where the streams are so we can burn them in, or we know where the lakes are so we can bowl them, or we know where the boundaries are so we can fence them. And we have a whole document that identifies key use cases for different morphologies of dendritic, deranged, or combined type. This is an important discussion that we will go back to in the following webinars as we dive deeper into specific implementation issues. Before we wrap up today's webinar, here are a few final thoughts. ArcHydro is constantly evolving. We are currently working on moving all network-based functions into Pro, adding more capabilities for H&H model integration, and pushing workflow tools for hand processing and national water model integration into ArcHydro Build, and add as much additional documentation as we can. If you have some specific workflows in your practice that you think ArcHydro can help with, please let us know. Maybe we have some possible approaches that are not well documented and we can point you to. Or you can highlight an interesting capability that we do not have yet and should consider for future development. There are several ways to get involved with ArcHydro. The best is to just get it and start using it. The GeoNet page is the best jump-off place, where you can get the tools, documentation, and share experiences and post questions related to ArcHydro. Or you can contact our team directly via email. The Water Resources Industry page and the ArcHydro landing page will also have some additional user stories about application of our technology in the water resources arena. And finally, let me quickly set the stage for the other presentations in the series. On March 11th, we'll dive into flooding and forecasting aspects of ArcHydro implementation. On March 25th, we'll talk about hydrology and ArcHydro, and we'll introduce some new exciting tools for hill slope analysis. And on the April 15th, we will focus on integration with external H&H models and model integration in general. And with that, let me answer some questions that came in during the webcast. The first set of questions deals with NHD and NHDPlus data. How much of dependency exists, if any, between ArcHydro and EPA USGS standardized hydrological datasets such as Watershed Boundary Dataset and the National Hydrography Dataset? There is no direct dependency between ArcHydro and NED, NHD, and WBD, but they can all be used as input data within ArcHydro data model and can be used with ArcHydro tools. Next question. Were ArcHydro tools used to develop NHDPlus? No, ArcHydro tools were not used to develop NHDPlus. But with ArcHydro tools, you can both develop NHDPlus-like data from your own inputs or use NHDPlus data directly within ArcHydro tools. And the final question here. Does Esri provide tools to make use of NHD data? ArcHydro is the toolset to use to mobilize both NHD and NHDPlus data. In fact, the first implementation of ArcHydro developed at the University of Texas was using NHD data. And I still use the dataset in my classes as an example of longevity and validity of the ArcHydro data model. The second set of questions deals with details on snapping distance within the watershed delineation tool used in the demo. Why is the snap distance important in the watershed tool? Well, often the interactive point placed by the user on the map will not be exactly on the stream. Snapping is then used to snap the user point onto the stream and delineate from the snapped location. The snapping distance defines the maximum distance allowed to move the point in the process of snapping. If too small, the snapping might not find a nearby stream. If too large, it might snap on a wrong stream. The next question is, how do you know what snapping distance you need? Snapping distance depends on two key things. First, cell size of your DEM. Watershed delineation is driven by flow direction, which is in turn derived from the underlying DEM. So the bigger the DEM cell, the larger the snapping can and should be. And second, how well you have placed your point. If you placed your point exactly where you want it, you do not need to snap at all. I prefer to carefully zoom to my location of interest, place my outlet precisely where I want it, and then not snap at all. And the final question in this group, do you have input on how to determine snapping distance? Well, that flows from the two things I just discussed. I normally do not like to go larger than 5 cell sizes of your DEM, so if my underlying DEM is 30 meters, I would limit it to 150 meters. I also often use a flow trace tool first. I click on a location somewhere upstream from my point of interest, get a trace, then zoom in and place my point in the flow trace result closest to my point of interest, and then delineate the watershed without any snap. Next group are some miscellaneous questions. Can ArcHydro be used on a micro scale? Yes, input to ArcHydro can be any scale data. Can trace be used to trace pollution points and potential affected areas? Yes, downstream trace can be used to trace anything moving downstream. If you are dealing with groundwater, you can use the flow direction derived from piezometric levels, and that will give you first approximate of pollutant movement. Of course, under steady state conditions and non-reactive pollutant. And how does ArcHydro account for constructed infrastructure such as ditch diversions where water might be pumped against the natural gradient of the terrain? Well, to account for such occurrences, you would probably use ArcHydro stormwater model that allows combination of overland flow and man-made structures. In the case of a pipe, canal, or aqueduct, the digitized direction of the line would indicate the direction of the flow of water. And when using geometric or trace networks, you can force the resource to follow or go against the digitized direction. And the final set of questions. Is there any advantage of ArcHydro when compared to HEC RAS? Well, these are two different systems, and we'll talk more about this in our fourth webinar when we talk about the integration of GIS with external H&H models. Are there any functions, tools that were not migrated from ArcHydro into ArcMap to Pro? Yes, while there are over 200 functions both in ArcMap and in Pro, there are some functions that have not been moved yet and still are on migration path. Some of the tools will not be moved at all, they might be deprecated, and some that are in Pro will not be moved to ArcMap. So if you have some specific functions you are concerned about, please get in touch with me and we can discuss the migration plan. And the final question: is this terrain processing a model builder tool that is included in ArcHydro toolset? This refers to the model builder we ran or discussed during the demo. Yes, the model builder that I demonstrated in the demo section of this webinar is part of ArcHydro tools. Most of the terrain pre-processing workflow tools have been published as model builder models. The idea was to give you a good starting point so that if you want to tweak the standard methods to suite your data, you can easily do that. And that concludes our first webinar. Thanks for participating and hope to see you on our next one.